Okay, do you have any questions before we start? Now, today we will start with the ensemble theory. I just would like to warn you that we will be switching back and forth between various descriptions of the same system. One of them is the thermodynamic description. Remember we said that, well, basically we have the du, U being the internal energy, was TdS minus PdV plus mu d, and well, we will see other terms in this expansion. And now we also looked at some statistical description where we identified the number of microstates corresponding to a given system, to a given macrostate. And now we said that, okay, the entropy, the thermodynamic entropy is given by this logarithm of this number of microstates available to the system. Now we start with the ensemble. Now the basic idea of the ensemble is you don't look at a single system, but look at many identical copies of the same system and look at the statistics of this ensemble or collection of many identical copies. That is what we will do. Now, how do we form this many copies? Well, one way, if we can do it, look at the system. You have your system at t equal to 0, let's say. T equal to t0. Look at the same system at t equal to t0 plus epsilon. Look at the same system at t0 plus 2 epsilon. And just make many such identical copies of the system. If the system is in thermodynamic equilibrium, in that case, the macroscopic properties are not changing in time. So if we want to calculate some or measure some property of the system, this property of the system will actually be a measurement over some time. But this averaging over time is nothing but somewhat different times of whatever this quantity is, f, divided by the total time. But our system at different times is just different copies of my system that exist in my ensemble. So this is actually the same thing as an averaging over the copies in my ensemble. So in that sense, if we want to find some experimentally measured quantities, we can construct this ensemble and treat that experiment. What we will measure in the experiment will be basically the ensemble average. Now, of course, this construction requires that I know what my system is at t equal to t0, t0 plus epsilon, t0 plus 2 epsilon, which assumes that I can solve the equations of motion, etc. That is something I want to avoid. That is not something I would like to make. So first I define, to avoid this construction, well, let's look at this phase space of my system. Now, when we say the phase space of my system, I'm looking at microstates of my system. And how can I specify the microstate of my system? In classical physics, it can be if I know the position and momentum of all my particles at a given time, then I know the microstate completely. So that is a point in my phase space. So in that case, my phase space will be this multidimensional space whose each axis corresponds to either some coordinate of some particle or the momentum of the same particle. That when I say phase space, that is what I can understand for a classical system. Well, for a quantum mechanical system, we have this, a system will have many quantum numbers. So a phase space, you can just treat the phase space as the space of possible quantum numbers. So each axis in that case will be the axis corresponding to the possible values of that particular quantum number. Now let me stick with the classical description for the time being, because most of them will be valid also in other descriptions. Now, what will be this, my system? Well, let me show it as P and Q. The horizontal axis is basically corresponds to all the momentum properties, momenta of my particles. The vertical is the space components of the position of my particles, all of them, 3 and in the horizontal, 3 and in the vertical dimension. So any microstate will basically correspond to a point in this phase space. So if I know this point, then I know the microstate of my system, because that point specifies all the momenta and all the coordinates of my system. Of course, that point will be moving in time. So if I have many copies of the system, in principle, they will be all in different microstates. So I will have all these points corresponding to copies in my ensemble. All of them will be moving in some direction determined by the dynamics of my system. And then when I talk about the ensemble average, well, I can just take each point one by one, calculate whatever f is corresponding to that point, sum them all up and divide by the total number of points. Or I can do another thing. I can say that, okay, rather than calculating f for each one of those points one by one, I can calculate f as a function of the microstate. And then I can ask the question, how many copies are there at that point P and Q? So let me call that some density. Well, it might be changing in time, because remember, all these points are moving around. So this is my ensemble average. And I will assume rho PQ to be 1. It's not the number, it's a number density of all the points in my phase space, but it's normalized to 1. So I don't need to divide by the integral of rho. If I don't impose this condition, the ensemble average will be basically this one. Let me also write the measure. So I don't think that is connected to the generator. Okay. No, the electricity, we are having a problem with the electric grid. Okay. So I see this, you can interpret rho to be the number density. In that case, this is how you define it, the ensemble average. So the numerator is just the total number, the denominator is the total number of copies you have. The numerator just gives the number multiplied by the whatever the value f has at that particular point, or you can just normalize rho to 1. So in that case, in a sense, it will be a kind of a probability. But the difference is just an overall constant, which is the total number of copies we have in the ensemble. Now, any questions in this average?
So, how I imagine the ensemble is, I don't know if it's correct or not. For every point in the phase space, we have a microstate. So, the ensemble, what ensemble does is like there are a lot of intermediate phase spaces, and every one of them has one point in it. And we sum them up to have the whole system as like this.
Well, you see, what we are having is you have your system. You just imagine you don't have one system, but millions of them. Each one will have its own microstate at a given time. So that is what the ensemble is. So since each of them has a particular microstate at a given time, they correspond to a point in phase space. Each of these copies, in principle, they can be in different microstates. So they will be different points on this phase space.
Can there be two microstates that are interacting with each other?
You see, in this ensemble, we are assuming that these microstates, well, let's say, for the time being, we will first assume that these copies are not interacting with each other because they don't really exist. That's just a mathematical, we are imagining infinitely many copies. But what we know is if the system is in equilibrium, in that case, all these copies will be more or less the same macrostate. They will not change in time. Now, of course, we will come to, as we study, there will be some copies that have a different macrostate, but they will be very few. The majority, the dominant majority, will be in the same macrostate, and hence, if you just pick one randomly, it will be in the macrostate that you specify. Now, our next task would be, okay, so in principle, we can define such a rho. We still don't know what it is. What else can we say about this rho, which is the number of microstates in phase space? So we have all these points moving around in our phase space. How does it change in time? But we know one thing, is every point corresponds to one copy of my system in the ensemble. The number of copies in the ensemble are not changing, they are fixed. So if I imagine some volume, just take some volume in phase space. This can be any volume that you can imagine, up to you. Well, the number of points in that phase space will be given by just rho of p cubed at a given time t, integrated over that volume. Now, as these points are moving around, this number within that volume might be changing in time. Now, there is nothing that tells me that the number within that volume should be constant. It will be changing in time, in general. But you see, if the number of points within that volume is changing in time, it basically means that some of those points are moving through the surface of that volume. So there will be a flux of points passing through my surface. And that will be the total number of points passing through my surface will be just the flux multiplied by the area element integrated over the boundary. Now, I will choose this area element. Will be just, let's say, this is dA at that point. It's just pointing outward. So if that flux is positive, it just means the number of points within my volume is decreasing. So these two, they have to be equal to each other with a minus sign. So you see, if you have just this number of points moving around, you imagine a hypothetical surface, mathematical surface. Now, if the number of points within this surface is changing, it basically means that those points are passing through the surface of my volume, because I already said that the number of points is constant. But basically, this is our conservation law. This just tells me that the total number of points is conserved. It doesn't change. Now, this J, this is the number of points passing through an area per unit time. It is nothing but rho, the density, times the velocity at a given point in phase space. And I would like to say that this velocity has the components p dot and q dot. So I can write that equation as, okay, so one thing, on the left-hand side, I have a total derivative because I'm integrating over p and q. The only thing that remains is t. But if I want to move that t inside the integral, that becomes a partial derivative. This is the left-hand side. I will be adding the other term, plus rho v dot dA over the boundary. This should be 0. Now, an integral over a closed surface, I can write as an integral over the volume by the divergence theorem. This should be equal to 0. So since this is valid for arbitrary volume, you see this integral equation is valid for arbitrary volume. So the integrand, if I just combine them, the integral is just this one. This has to be 0. You see, I'm not doing any statistics. I'm not doing any statistical mechanics. This is just a direct consequence of the mechanical laws. Just take many copies of your system, identify the points in phase space, define some kind of a density. That density should satisfy this equation, whether the system is in equilibrium or not. Now let's continue. You see the divergence, rho of v, is in ordinary space, in three-dimensional space. The divergence of any vector field is basically take the x component, take the derivative with respect to x, take the y component, derivative with respect to y, take the z component and its derivative with respect to z, and sum them up. Just take each component, take the derivative with respect to that component, that direction, and sum all of them up. Now the x, y, z in phase space are just p's and q's. So this will be equal to del over del pi, rho of pi dot, plus del over del qi, rho qi dot. That is the time derivative. Which will be equal to del rho over del pi, pi dot, plus del rho over del qi, qi dot, plus rho times del pi dot divided by del pi plus del qi dot over del qi. I just took the derivatives. Now first, let's look at this term, this sum. And remember, these are just coordinates in classical physics. They have a Hamiltonian, they satisfy the Hamiltonian's equations of motion. So dpi dot by del pi is del over del pi, pi dot. But now I know the Hamiltonian's equations of motion. Pi dot is nothing but the minus the derivative of Hamiltonian with respect to qi. Now, h is the Hamiltonian of my system. I'm first taking its derivative with respect to qi and then with respect to pi. But I can change the order of derivatives. Now again, I can use the Hamilton's equations of motion. This is the derivative of Hamiltonian with respect to pi is nothing but qi dot. Well, the only thing I use is the Hamilton's equations of motion. Again, I repeat, I'm not doing any statistics here. I'm not doing any approximation. I'm just saying that my system has a Hamiltonian and it satisfies the Hamiltonian dynamics. But this tells me that the second line in the divergence of rho of V, that is zero. So divergence of rho of V is just del rho over del pi dot plus del rho over del qi dot in general. And remember our first equation, if I add the partial time derivative of rho with respect to t, this should be zero. But also keep in mind that this is nothing but the total derivative of rho. So what this tells me is that, you see, we have all these points in phase space. They are moving around. So just pick any one of them, any one you like. And that point will have a time-dependent momentum and coordinate pi of t and qi of t. So if you are moving with that point, and you are looking at how the density changes as you are moving with that point, it doesn't change. This is what this equation tells me. Now let's go one step further. You see, pi dot is minus del h over del qi dot is del h over del pi. So this equation I can also write as del rho by del t plus del rho by del qi del h by del pi minus del rho by del pi del h by del qi equal to 0, or del rho by del t plus rho and h Poisson bracket, this is 0. Well, when we do the quantum version, this just becomes the ordinary commutator. Again, I repeat, up to here, I didn't make any assumption. This is valid for any system. I'm just saying that the only thing I'm saying is that just imagine many copies of your system. Each one of them corresponds to a point in phase space. And for those points, define a density. That density should satisfy this equation, whatever the system is. It can be in equilibrium, it can be out of equilibrium, it can be very complicated, it can be just a few particles, etc. It should satisfy this equation. Now, when we talk about equilibrium, we will say that, okay, the system shouldn't be changing in time. So that we will say that this is 0. For a stationary system. And if you have a system in equilibrium, that will be stationary, so this has to be satisfied. You see, for example, here, there might be external effects influencing my system. All of them are within the Hamiltonian of my system. So as long as Hamiltonian dynamics is satisfied, these equations are valid. I can say that the various copies in my ensemble, they might be influencing each other. This equation will still be valid. Because the only assumption I made, besides defining this rho, the only thing I assume is that my system satisfies Hamiltonian dynamics. So for a stationary system, we have the Poisson bracket of rho with Hamiltonian should be 0. Now there are many, now This is a condition that we impose on rho for a stationary system. We don't know what rho is. One way of constructing this rho was just taking these copies of my system at various times. In that case, ensemble average will be exactly equal to the time average, and we are done. But we don't want to evaluate the time evolution of my system. So we don't know what rho is. Well, the easiest choice, the simplest choice, rho is constant, but we impose the energy is conserved. If let's say I will be assuming that the Hamiltonian and the energy have the same form. If the Hamiltonian or the energy of the system is given to this macroscopic energy, then rho will be a non-zero constant, and rho is equal to zero otherwise. So this is how we define the microcanonical ensemble. But keep in mind that, okay, we are constructing this, we are studying this mathematical construction. It's a mathematical construction where we have these many copies of my system, but at the end of the day, what I would like to study is what I will measure in the experiments. That is more or less the time average. So by saying that, okay, microcanonical ensemble describes my physical system, I'm making assumptions over here, such as if in the microcanonical ensemble, the distribution should resemble the time evolution. So basically, since here I'm saying that my ensemble is uniformly distributed over all microstates available, consistent with the restrictions imposed, like energy is conserved. It's uniformly distributed. Well, if I interpret it as time averaging, well, that basically means that with time, my system basically evolves and passes very close by every possible microstate consistent with my construction, my constraints like the energy, or if my system has a total momentum with the momentum. This is what's called the ergodic hypothesis.
Can you repeat how do you understand that because of rho is constant, then we have microstates are evenly distributed over our
Well, what do you mean? I'm not saying microstates are evenly distributed over the phase space. You see, energy conservation. If my system is isolated, energy should be conserved, and that basically tells me that not all of my phase space is available. Only the part of the hypersurface in phase space which corresponds to that conserved energy is available. And here in the microcanonical ensemble, I'm basically saying that rho is constant on this surface. But constant means uniform. So that's basically the definition of uniform. Other questions? Well, if rho is constant, the ensemble average of any quantity will be basically just evaluate that over available phase space, available meaning that not all phase space will be available because of conditions I have like the energy conservation, and divide by all the energy, by all the volume of my phase space. So let's apply this to our favorite toy, the ideal gas. Well, before going to the ideal gas, okay, so we have this ensemble averaging. How do you relate it to statistics? You see, we had this statistical description. We said, okay, let's count the number of microstates. So how do we count the number of possible microstates in phase space? Well, one typical guess would be capital omega, which is the number of microstates available. I have small omega, volume of phase space available. One guess would be they should be proportional. If the phase space is larger, in that case, the phase space is larger, the number of microstates will be larger. Well, what is this proportionality constant? Let's just say omega 0. Okay, classically, omega 0 just doesn't exist. So that was one problem before the discovery of quantum mechanics. So we only had the proportionality. Omega 0 was some kind of a hypothetical regularization, let's say. Now, quantum mechanics has an explanation for what omega 0 should be. Okay, on one hand, we have the uncertainty principle. Which basically states that delta p times delta x, just take any momentum and a corresponding coordinate, uncertainty in each one of them, the minimum possible value is something of the order of Planck constant. Well, this basically, quantum mechanics basically tells us that you cannot identify points in phase space because the points will be, the microstates will be blurred in a sense in phase space. They will occupy some volume h. So one guess would be omega 0 should be something related to, for the time being it's just a plausibility argument, let's say. It should be somehow related to h. Well, for each dimension we have an h. If we have n particles, then we have 3n dimensions in phase space, h to the power 3n. This is what one would expect. Well, this is just an order of magnitude estimate, let's say, from quantum mechanics. It doesn't tell us the exact value, but we will derive the exact value. Now, once we make this identification over here, in that case, we know that the entropy, which was defined as k, l, and omega, will be k, l logarithm of omega over omega 0. So now we have a connection also with the statistics. So once we have the entropy, we know everything else. So let's look at omega for an non-interacting particles in three dimensions. Now you might have systems where you restrict the motion of your particle in 2 dimensions or even 1 dimension, like electrons in some solids. How can we calculate omega? Sorry. One can calculate omega. It's just a phase space volume restricted to energies. Let's say the energy of my particle, my system will be p squared over 2m, or pi squared over 2m, sum over all I. Well, this should be a given value, but if you consider physically, you cannot fix the energy of a given system completely. So basically, we need to evaluate this bit within a very thin shell from E plus delta over 2, between E plus delta over 2 and E minus delta over 2. Delta is the uncertainty in our energy measurement. This is what our omega will be. Now, you see, this condition over here doesn't depend on Q, so the position of the particles. So I can integrate over the position of all my particles. And the integral over the position of each one of the particles will just bring me a factor v. I have n of them, so this is v to the power n. So I have d 3np. Of course, with the condition that pi squared over 2m, or let me write it slightly differently, sum over pi squared should be within this range. So this is.
Are they smaller than equal to or strictly not equal?
What will be the difference?
I guess there will be a difference if we, let's say in the book they try to calculate for harmonic state and h of delta is hw, and then it should be equal at some energy level.
Well, you see, I'm doing classical physics. There's no h bar omega yet. So I'm just calculating my volume of this very thin shell in phase space. You see, adding the surfaces doesn't change the volume, or subtracting the surfaces doesn't change the volume. But of course, if I'm seeing this discrete nature of states, then I might say that, okay, there will be some states right at the surface, if it's possible, if you are looking at the discrete states. And in that case, whether you are counting the surface in your number of microstates or not, it will make a difference. But here I'm not counting the number of microstates. I'm just calculating the volume. I'm in classical physics. Okay, now we have this problem of, you see, this pi squared, sum over pi squared is equal to some constant. It's just a sphere. In this case, it is a 3n dimensional space. I need to calculate the volume of the sphere. I have, you see, the upper bound gives me a sphere. From that larger sphere, I'm just extracting the inner sphere. And what remains is a shell. So what is the volume of a sphere in n-dimensional space, in 3n dimensional space? So that is something I need. But before continuing, you see, omega is proportional to the v to the n, and since the number of microstates is proportional to this small omega, already we have the number of microstates proportional to the v to the n, which was something we had studied in the previous week. So we are already in a territory that we already know. So let's calculate that 3n dimensional volume. Let me just write it in this form. What is this volume for a sphere of radius r in 3n dimensions? Well, just with analogy with 3 dimensions, the easiest way would be to go to the polar coordinates. In polar coordinates, this will be dp times p to the power 3n minus 1 times whatever solid angle I have. And this p goes from 0 to r. So this will be r to the power 3n divided by 3n integral over b omega. Okay, what remains is what is the complete solid angle in 3n dimensions. Well, in 3 dimensions, it's just 4 pi. But in 3n dimensions, it will have a more complicated expression. Let's do a trick. You see, here we are trying to evaluate an integral whose result we don't know. Let's apply the same principle, meaning going to the polar coordinates, to an integral that we already know. Let's look at this one. In a 3n dimensional space, let me evaluate e to the power minus x squared. Now, this will be nothing but dx1 e to the power minus x1 squared, dx2 e to the power minus x2 squared, dx3n e to the power minus x3n squared, from minus infinity to infinity. It's just a Gaussian integral whose result is square root of pi. So this will be equal to square root of pi. I have 3n of them, so this is pi to the power 3n over 2. Okay, on one hand, I know the result of this integral. This is pi to the power 3n over 2. At the same time, I can go to the polar coordinates. In polar coordinates, the same integral will be this one, dx, x to the power 3n minus 1 from 0 to infinity, d omega. Let me write 3n over here. Okay, again, on one hand, I know the whole result. I can evaluate the x integral. I also have a e to the power minus x squared. Well, this basically tells me that this 3n dimensional solid angle is square root of pi to the power 3n divided by 0 to infinity dx x to the power 3n minus 1 e to the power minus x squared. Now the only thing left is what is that integral over there? I can convert this to this integral. You see, this is an integral that you will see. Whatever you do, if you do any computation, this will be an integral that you will face. This is nothing but the gamma function. Or for integers, this is just n minus 1 factorial. Now I can convert my integral into that one by just identifying y is equal to x squared, or x is equal to square root of y, and dx is equal to dy over 2 square root of y. So my integral from 0 to infinity dy over 2 square root of y, y to the power 3n over 2 minus 1 over 2 e to the power minus y. So this is equal to 1 over 2 from 0 to infinity dy, y to the 3n over 2 minus 1 e to the power minus y, or gamma 3n over 2 minus 1. So the omega 3n, you see, I have pi to the power 3n over 2 divided by that integral is, well, I have a 2 gamma 3n over, sorry, not minus 1. Gamma 3n over 2, or 2 pi to the power 3n over 2 divided by 3n over 2 minus 1 factorial. Okay, so now I have the factorial also. So if you go back to what is our omega, you see this is our omega on the first line over there. Where p in 3n dimensions, p squared is less than 2m e minus delta over 2, larger than 2m e plus delta over 2. No, it's the other way around. So this will be v to the n. I can write the volume, which will be 2 pi to the power 3n over 2 divided by 3n over 2 minus 1 factorial. Radius is 2m e plus delta over 2 to the power 3n over 2. What I'm using over here is just this result over here, 3 over 3n. Minus e minus delta over 2 to the power 3n over 2 divided by 3n. So this is my omega. I would advise you to go over these computations on your own, and following somebody else doesn't really teach you much. Well, delta will be much smaller than E in general, so we can do a Taylor expansion. Also remember when we were looking at the ideal gas before, we said that delta will be very small than E. We Taylor expand, and in fact, the volume, all of the volume, will be more or less determined by the first term, not the second one, the surface area. So this will be V to the N 3n over 2 minus 1, 3n outside. So this will be well, you can just imagine this function to be the Taylor expansion of 2m e to the power 3n over 2. So the first term will be just take the derivative. That will bring take the derivative with respect to e, 2m e to the power 3n over 2, divide by e, multiply by 3n over 2 times delta. Okay, that's kind of a boring, tedious, straightforward computation, but it's something you should have among your abilities. Now, we identified omega. We already know number of microstates from the previous week. I can just compare the two. Which one is what? You see, from the previous week, I know capital omega, which should be equal to capital small omega over omega 0, which will tell you what omega 0 should be. And indeed, it turns out that omega 0, just compare with our previous result, omega 0 is h to the power 3n. I said before, just using quantum uncertainty principle, we said that omega 0 should be something related to h to the power 3n. Because in phase space, in P and Q space, we cannot localize any microstate to a volume less than h cubed for a single particle. So if 2 points in phase space are within that volume, we cannot say that they are distinct states. Uncertainty principle doesn't allow it. Now we have a rigorous derivation that for the ideal gas at least, that omega 0 has to be equal to h to the power 3n for quantum mechanical description to be consistent with the classical description. Any questions?
The thing is, if we try to localize particles between that length, then there can be a problem about then the particle cannot be stay as a single particle because we have a production that's 3m squared.
Now, you see, here we are doing a very simple model. We just have non-interacting point particles. That is our system. At least for this system, this is the rigorous proof that omega 0 has to be equal to h to the power 3n. Now, in the next hour, we will look at the harmonic oscillator. We will look at the quantum mechanical description, this description, at least for 1 degree of freedom. And in that case also, we will see that it is omega 0 is h for 1 degree of freedom. And there are also various experimental measurements which say that omega 0 should be h to do something. You see, if you want to do statistical physics of classical systems, even in that case, to be consistent, we have to somehow deal with the Planck constant. Planck constant even arises there. Okay, let's give a 10-minute break so you can also wake up after this derivation. And we will continue after 10 minutes.